some linear differential equations, let's go ahead and look at an example of an application. It's called the mixing problem. In the mixing problem, we have a tank, and there's some mixture of salt water or some other type of mixture being poured in, and there's also some mixture leaving it. The way the problem is usually going to be set up, you're going to be given a rate at which stuff is coming in, the mixture, and a concentration of that mixture. The way you're going to find out how much salt is coming in and out is you're going to take the rate and multiply it by the concentration. What that's going to do is give you a unit of kilograms per second, right? Because the liter and the liter are going to cancel each other out. And when you have the kilograms per second, that's the unit that you want. That's the quantity that you want, the quantity of salt, the change in salt per unit time. Okay? So the way we're going to do the problem is very simple. We're going to set up a differential equation. We're going to say the change in the amount of salt, Q is representing the amount of salt in our tank. The change in the amount of salt is just the rate at which the mixture is coming in times the concentration of the mixture minus the rate at which the mixture is going out times the concentration of that outgoing mixture. Now that is going to give us an answer, but it's going to have a constant. And to get rid of that constant, we're going to make use of what's called a boundary or auxiliary condition. And that's basically restricting how much we start with. That's basically saying, okay, but you started out with this much salt, so here's your actual solution. And that's going to get rid of the constant. Let's actually go ahead and do an example to see how this plays out. So here we have a tank of 10 liters, and there's some rate at which stuff is coming in and out, and some concentration, and some beginning quantity of salt. So let's go ahead and first set up our differential equation. dq dt is going to equal the rate at which stuff is coming in times the concentration that's coming in. Well, the rate is 2 liters per second, and concentration is 2. So it's going to be 2 times 2, 4 kilograms per second. I'm going to drop the unit, but I suggest, just because I don't want to carry it over the board, but I suggest you keep it in your calculations. It's very convenient, and it's a nice way to make sure you don't make mistakes. So now let's do the outgoing stuff. It's constant. It's the rate at which stuff is going out times the concentration that's going out at. The rate is still 2. Now the concentration, we're not given a C out, and that's usually going to be the case. Instead, what we're going to be given is the statement somewhere in the problem that the mixture is well stirred, or that the salt is spread evenly throughout the mixture. And what that means is you have a uniform mixture, and the way you figure out the concentration or the density is just take how much salt there is, Q, over how much mixture there is, 10. Okay? So our answer is going to be, our concentration times rate is going to be 2 times Q over 10, or Q over 5. And again, we got the concentration by saying, well, I have Q kilograms of salt, and it's spread out over 10 liters of mixture. So that's my concentration, okay? So here is our differential equation. It's pretty simple. We can go ahead and get started on solving it. I'm going to move the Q over 5 to the other side. And now I'm going to introduce my integrating factor. It's going to be e to the integral of 1 over 5, or just e to the 1 over 5 t, 1 over 5 t. So I'm going to multiply everything by it. Q prime plus Q over 5 e to the 1 over 5 t is equal to, and don't forget to multiply your right-hand side by your integrating factor. So now I have this guy, and I notice that my left-hand side is a direct result of product will apply to this expression. And I'm going to write this. And now I'm actually ready to integrate, so I'm going to integrate both sides. So on the left-hand side, I'm just going to be left with e to the 1 over 5 t times q. And on the right-hand side, I'm going to integrate this guy. Well, the 1 over 5 gets flipped and comes out, so I get 20 times e to the 1 over 5 t plus c. Okay? Now, to get rid of that plus c, we're going to impose this boundary condition that says at time equals 0, our quantity is going to be 2 kilograms. So we're going to say, okay, well, at time t equals 0, then I'm going to have, okay, actually, let's solve for q first. So we're going to have qt is equal to 20 plus c times e to the minus 1 over 5t, because I just divided by e to the 1 over 5t. I divide both sides by that expression. So now we can actually go ahead and plug in our boundary condition, and at time t equals 0, we're going to have 2 equal 20 plus c times e to the blah blah 0. So it's just c, because that e to the blah blah is going to be 1. So c is obviously minus 18. So our real expression without any constant is going to be 20 minus 18 e to the minus 1/5 t, right? So that's basically where some problems end. But some more complicated problems add a second sort of phase to the problem. They say at some time, here at time 30 seconds, we're going to change the rate at which stuff is coming in, okay? So now we're going to have another differential equation on top of this. So we're going to write it. Well, it's going to be, again, rate in times concentration in. Concentration in is just 2. Rate in is 3, so 6 minus. Now rate out times concentration out. Nothing has changed there, so it's just going to be q over 5 again. Remember, we just changed rate in. We didn't change rate out. It's still 2. So now, if you solve this, it's going to be very similar to this. In fact, you're going to get a very similar answer. You're going to get q of t is going to be 30 plus c e to the minus 1 over 5t, I believe, if I'm doing this right. So, right. Actually, it should be a minus. Yeah. Okay. Okay, that makes sense. So, now I'm actually going to change this to a d because I don't want it to interfere with that one, and I'm going to call this q2 and I'm going to call this q1. So if we want our situation to be modeled by two functions but have it be a smooth transition to where this one ends and this one starts, we have to make sure that where this guy ends at t equals 30, it equals where this guy begins at t equals 30, okay? So that's going to be our boundary condition. We no longer have this boundary condition where, that's how much salt we start with, but it's now going to be how much salt was there when this guy ended. That better be how much salt this guy starts with, because in an instant, nothing changed. Okay, we just changed the functions that we're going to be modeling this thing with. So what we're going to do is say q1 of 30 seconds is going to equal q2 of 30 seconds. Now, I'm not going to actually carry this out just because it's really, really algebraic and messy, and there's no point to it. But this is basically what your second boundary condition is going to be. You're going to plug in 30 into this expression and plug in 30 into this expression, and you're going to set them equal, and then that will allow you to solve for d, and it's going to be messy. It's going to have a bunch of e to the things and a bunch of constants, but you're going to be able to do it. Okay, so there you have it. It's a very involved process, but if you're sort of careful with your variables and do it sort of methodically, it shouldn't be that hard. So there you have it.